Hello, everyone. I'm Zachary Nickerson. I'm a product manager at Algolia on the retrieval and ranking teams. I've been working in AI search for the past 4 years, focusing on everything from vector search to RAG and now ranking algorithms. I'm Canadian, but recently moved to London, so I'm starting to think my personal ranking system is needing some serious retraining. Moving from terrible weather to, well, terrible British weather. But I digress. When I'm not working on ranking algorithms, I'm usually listening to music, and every music geek knows how this goes. You start getting into something semi normal, like techno, for example. Then you evolve into more niche territories like French techno, and then before you know it, you're deep in the weird stuff. You're listening to French industrial cyber techno at 3 a.m. But here's what's remarkable. Somehow, the music apps I use not only find relevant tracks for these hyper specific queries, but they consistently surface some of the best French industrial techno I've ever heard. I seem to find great and relevant results even when searching for phrases like that. But how do they do it? Well, that's exactly what I want to cover today. How we built a system that can rank results intelligently even when dealing with niche or specific queries where you don't have that much interaction data to work with. So in search, we're really good at using real user behavior, the clicks or views and conversions or plays, for example, to understand what people actually want. But what happens when you don't have that data? We'll answer that today. Let's meet the main characters of our story. The key concepts you'll want to keep in mind here. So think of this as like a classroom setting. So on the left there, you've got dynamic re-ranking. That's the teacher. Dynamic re-ranking is an Algolia product that learns from real user behavior to optimize rankings for popular queries. It's experienced and reliable, but it's limited to scenarios where it already has that information or that data. In the middle there, you'll see learn to rank. This is the methodology. So learn to rank is a well-established machine learning technique. It's not Algolia specific, and it takes the teacher's knowledge and formalizes it into a repeatable process. So we've built on this approach to make it work for our platform. And then on the right-hand side there, you'll see multi-signal ranking. Think of this as like the student. So multi-signal ranking is Algolia's newest ranking product, and it learns from DRR, so the teacher, and it uses LTR, the curriculum, to apply that knowledge to entirely new queries, so even ones the teacher has never seen before. And as we go through this presentation, I'll use consistent visual cues to help you follow these three concepts and see how they work together to solve tough ranking challenges. To tackle this long tail ranking problem, we needed to start with something that already worked. So that something was dynamic re-ranking. So dynamic re-ranking is beautifully simple. It's essentially the wisdom of the crowd, but just applied to search results. So when people consistently interact with certain results for a query, whether that's clicks and purchases in e-commerce or plays and saves in music streaming, for example, dynamic re-ranking learns those patterns and automatically boosts those results. The magic is really in its simplicity. No complex configuration, no manual rules to maintain. Dynamic re-ranking just watches user behavior and it says, hey, people really seem to engage with this result when they search for this term, so let's put that up higher. So think of how Spotify learns when people search for chill beats. They consistently play and save certain tracks over others. Dynamic re-ranking works in this way. So it identifies these engagement patterns and then applies that to improve the ranking. And it works incredibly well. Our users consistently see improvements because dynamic re-ranking is capturing the real user preferences and not just the ranking that we think will work well. As you know, most search applications experience the 10 to 20 or 80% rule. So you have about 10 or 20% of queries that users search for frequently. So in a music context, this would be like your pop, your hip hop, your rock type of queries, the mainstream stuff. So these mainstream type of queries accumulate the rich behavioral data that popularity-based ranking algorithms can leverage, and they can leverage it beautifully. But then you have that other 80%. So it's all those queries that happen less frequently for searches like ambient gaming music with female vocals. I don't know, you might be into that. You might not have enough user interaction data there. So this creates what we call the long tail cliff. It's a huge portion of queries where popularity based ranking just simply can't operate because users haven't generated enough signals yet. But here's why that matters. These niche searches, the ones like the ambient female vocal one, they often represent users with the highest intent and engagement. So when someone searches for something that specific, they know exactly what they want and they're more likely to really deeply engage with that kind of content. So the challenge is like, how do you surface all those quality results for the long tail queries, but when you don't have the behavioral data that traditional ranking relies on? That is where our next character comes in and our machine learning approaches become essential. So, learn to rank models treat ranking as a supervised learning problem. We train them on query document pairs where they already know what's relevant, so like the past. But unlike typical machine learning algorithms or models that predict exact values, learn to rank is trying to predict to get the order right. So the goal isn't a perfect score, it's just better ranking. So I'll give you a concrete example. Imagine a user searches for sci fi movies with time travel. The model analyzes features like ratings, genre tags, release year, the number of reviews that the movie has. So basically, all the things that you'd naturally weigh when ranking results. And instead of us hand tuning those weights, Learn to Rank is going to learn patterns automatically from thousands of past ranking decisions with the other movies. So the magic is that these learned patterns, well, they transfer. So even if the query is something that the system has never seen before, like German films that make you laugh, it recognizes similar feature combinations, genre tags, critical acclaim, Rotten Tomatoes rating, age rating, etc. And then it applies what it's learned from the related queries to deliver great results. Learn to Rank was designed to tackle the long tail ranking challenge we talked about earlier. But building it wasn't just about theory. We had to make some critical engineering trade offs and design decisions to make it work at the Algolia scale. There are three main approaches to Learn to Rank, and they work in fundamentally different ways. So on the left there, we have pointwise. Think of this as like predicting individual movie ratings. So the model independently learns that, this movie is a 4.2 and that one's a 3.8, and it ranks by sorting those scores. It's simple and computationally efficient, but it doesn't capture what really matters, which is the relative order. So two high scoring movies could both be irrelevant for a query, but the model wouldn't catch that. The second method is called pairwise. So this method learns preferences between pairs of items. So given two movies, it figures out, okay, movie A should rank higher than movie B for this query. And it's actually better because it focuses on the ordering, like we said. But training requires comparing every single item to every other item. So that's big O times n squared complexity, which gets really expensive. And then the third there is called listwise. So instead of scoring or comparing pairs, listwise treats the entire ranked list as a single unit. So it's optimizing for the whole ordering at once. And it's asking, okay, from this whole ordering, what's the best possible order for these 20 movies for this query? So the key insight here was that metrics like NDCG, which is one of the main metrics we track at Algolia for overall relevancy, that metric cares about the order of results. So it's not exactly the scores assigned to them, but it's the overall order of results. And users care about seeing the most relevant results first. So even if the lower ranked items aren't perfectly scored, the search still feels successful. So that's why we chose a listwise method, because it directly optimizes overall ranking quality, not just individual predictions. So we already knew that dynamic re-ranking performs really well for popular queries. And now we know that Learn to Rank, especially the listwise approach, can directly optimize ranking quality and could leverage the popularity data. So we began exploring, okay, how do we combine that Learn to Rank with dynamic re-ranking, the teacher and the curriculum, and extend its intelligence to tackle this long tail ranking problem to the student. The less common searches where DRR has little, no data. So we already knew that dynamic re ranking performs really well for popularity queries. And now we also saw that learn to rank, especially the listwise approach, can directly optimize ranking quality and could leverage that popularity data that dynamic re ranking has. So we began experimenting how to combine the two and to extend the intelligence of dynamic re-ranking to tackle the long tail ranking problem. Those less common queries where dynamic re-ranking has little or no data. So this experimentation led to the creation of multi-signal ranking. So dynamic re-ranking already knows what works for popular searches. So multi-signal ranking takes those successful ranking decisions and learns from them. So it looks at all of the product's features and record attributes that contributed. So that might be, ratings or price, availability, brand reputation, and it finds patterns. And it learns. When these features appear together, users engage positively. Then, when a user searches for a long tail query like wireless noise canceling headphones for travel, multi signal ranking recognizes similar patterns and predicts which dynamic re-ranking would likely boost if it had enough data. So put simply, multi signal ranking just asks if dynamic re-ranking knew about this query, what would it do? And then it uses learn to rank to make that prediction happen. So research shows on learn to rank models that these models can actually handle hundreds of input features or record attributes, but including irrelevant ones can actually really hurt your performance. So the challenge is that, what's relevant varies widely across different domains, whether that's like a gaming index or a music index or an e-commerce website. Even like for a deeper example, you can imagine an academic learn to rank data set like MSLR relies on features like PageRank and, CTR, which they work well for web search, but then those signals are meaningless for when ranking products like in an e-commerce catalog or content in a media library. So at Algolia, being schemaless is really important for us, but it makes the challenge even bigger. So every domain has different features that matter, but the good news is that you know best. You know what makes your users tick, what makes people make a decision for this item or this item. You are the one who understands what drives user behavior for your specific use case. So maybe, for example, users are consistently choosing products with 4-star ratings and same day shipping. Maybe they prefer items that are on sale, but only if they're from trusted brands. And maybe even, sellers get a boost, but only when the number of reviews is high. So the model is learning these patterns from your actual conversion data. And that's why in multi-signal ranking, we made a decision to give you, as the controller of your own search, control over signal selection. So you can actually test these hypotheses. You can select the product attributes that you think matter most: ratings, shipping speed, status, brand reputation. And the learn to rank model learns how to weight properly and combine these signals based on dynamic re-ranking's successful ranking decisions in the past. Really, you know best. So let's talk about measuring impact. So when we apply these learnings, we can dramatically increase the total number of queries that get intelligent ranking. We take the percentage of queries with, re-ranking on them from about 20% of your total query volume to about 80% of your total query volume. Now, we can also increase the number of hits per query that are re-ranked. So you can imagine multi-signal ranking can combine with dynamic re-ranking on top when there's a thin number of re-ranked results, and it can actually create even more re-ranked hits for that single query. So we have both, horizontal and vertical extensions of reach for re-ranking. So now all these outcomes, metrics, they're fantastic, but you'd hope you'd have this functionality. Of course, it's baked in there. But then what happens? How do you iterate on those, and how do you improve your multi-signal ranking setup? Well, we do that through what's called reading SHAP values and improving your signals. So SHAP values, Shapley additive explanations. It's a method for explaining machine learning model predictions. So it shows the influence of each signal on a single result, or an average across all the results. So think of chat values as like a way to answer the question, wait, why did this specific song rank number 3 for the query, groovy nighttime shower jams, and the other one didn't? So the chat values might show that the song's BPM or its subgenre tags and its typical listening patterns and such are all contributing positively to its ranking, where another feature, the release date, maybe it's super old, contributed negatively. And in multi-signal ranking, we're trying to provide the visibility into these chat values so you can understand what signals actually have a strong impact. So either strongly boosting or strongly demoting results. And what signals are weak and probably should be replaced. So that's how you actually improve the system. And it's ultimately giving you two capabilities. It's first, you can see across your entire result set what are the signals that are consistently driving ranking decisions. And then maybe you also discover that, artist popularity for in specific is having much more influence than you expected, or that song length isn't really making a difference in your ranking at all. Now, second, for any individual result, you can see exactly why it ranked and where it did. So for that jazz song in position 3, you might see that it's 128 BPM and the chill jazz subgenre tag, and its evening listening patterns. They all contributed for this specific query. So this interpretability is pretty crucial, especially when you're working with these machine learning systems that are quite complex, because it allows you to debug, iterate, and improve your signal selection based on what's actually happening in the model rather than just guessing. So, looking ahead, the most interesting technical opportunity that we think is about extending multi signal ranking beyond just conversion optimization. So, right now, multi signal ranking is learning from the teacher, right? Dynamic re ranking, and it's learning specifically from its conversion focused ranking goal. But the underlying learn to rank model and the framework with it is really just goal agnostic. So you could just as easily train it on engagement signals, revenue optimization, or even things like content discovery metrics. So we're trying to build a system where you can define success and what that means for your specific use case. And, maybe you want to optimize for revenue rather than for conversion rate. Maybe you want to balance the, user satisfaction with inventory turnover. All this technical foundation, it supports that flexibility. And it's just a matter of changing the training labels and the optimization targets. So this turns ranking from a one size fits all solution to something that you can actually tune to business objectives or to objectives for whatever your use case is. So it's a more principled approach to ranking optimization that acknowledges that different platforms have different success metrics. And it leverages the same learn to rank technology to optimize for whatever matters most for your users. Multi signal ranking represents our approach to making sophisticated machine learning accessible to your ranking problems. We've taken an established learn to rank methodology and built practical tooling around it that lets you apply it to real world challenges. The key insights are giving developers control over signal selection, using existing behavioral data as training signals, and building these flexible systems that adapt to different use cases rather than just assuming that one size fits all. So, whether you're building content discovery, e commerce search, or any application where ranking matters, the principles we discussed, like leveraging behavioral data, applying LTR, maintaining developer control, they can all help you think about extending intelligent ranking across your entire query space. So we're just getting started, and we can't wait for you to experience what's coming next. Again, I'm Zachary, and thank you for joining, and enjoy the rest of DevCon.